for gases that can be described by classical physics. So, Maxwell and Boltzmann together came up with the that distribution and described basically, the kinetic theory of gases, and we showed how you can get some of the thermodynamics that was already known. So it's actually, more impressive that people had figured out a lot of that stuff without realizing what quantum mechanics was, or even, Kelvin was able to do a lot of stuff without realizing. Sorry, I'm trying to. There we go. Now I can see everybody except myself, which is good. Okay. So Kelvin and others, Carnot, were able to do a lot of like the classical thermodynamic stuff without ever having any kind of microscopic picture of what was going on. And then Maxwell and Boltzmann together were able to describe from a microscopic picture in the kinetic theory of gases what was going on. And so it fit with what was already known, which of course it had to. But then once people started understanding quantum mechanics, they're like, well, there's statistics about these different types of particles and what states they can be on. So namely bosons and fermions. So today we're going to start with looking at those quantum statistics. So first, let's look at what's the limitation of classical statistics. So we talked about last Friday that we can use the classical description as long as there's enough space between the particles, right? So if the space between the particles is bigger, much bigger than the de Broglie wavelength, we can say that they're not really going to have any sort of quantum overlap. So if we look at the Maxwell-Boltzmann distribution, we have that exponential factor that depends on energy and temperature, but we had that normalization, right? And I kind of glossed over the actual calculation of that normalization, but if that value is much less than 1, what it means is most quantum states are unoccupied, right? So so we're not looking at interactions in the sense of a force between particles. The only way that these particles affect each other is if like there starts to be, things start to fill up, right? So you might think of like if you're in a large movie theater or sports arena, if you went there right now, right, you'd have your pick of whatever seat, right, because nobody's supposed to be there, right? And even as things start to fill up, you're not really necessarily going to interact with anybody. Nobody's pushing you, right? But at a certain point, you can't pick just whatever seat you want, right, because they're full, right? But if the occupation number is really small, then you basically get whatever seat you want. But as it starts to fill up, then there's only certain ones left over. So that's kind of what we're looking at here.
Hey, Dr. Bartz.
Yes.
We have at least I do. I have like an edit equation box in the middle of my screen.
Yeah, same here.
Huh.
Okay. I don't know if it's from a different.
It might. Maybe I'm.
I don't. Yeah, it was just blocking the.
Let me. Okay. Let me. Aha. That's my other window. Okay. I'll close my other slideshows.
Thank you.
Yep. Okay. So let me go back and share this again. Okay, better? Okay. So so we're looking for under what conditions are most quantum states unoccupied or available, right? So so let's look at, okay, so we've got an expression for the kinetic energy of particles, right? So we're looking at non-relativistic, so kinetic energy is p² over 2m, which is approximately Boltzmann constant times temperature. Now we found that the average is 1/2 kT, or sorry, the most common energy was 1/2 kT, and the average energy was 3/2 kT. But if we're just kind of rounding and saying what's the scale of the energy, we can just use kT and not worry about that numerical factor. So momentum is going to be square root 2 times the mass of the particle times kT. So then we have the de Broglie wavelength, right, is Planck's constant divided by the momentum. So we can write that in terms of the temperature using that calculation. And the particle separation is, well, if we take the density of particles, right, the number of particles divided by the volume, that's going to be 1 over distance cubed. So if we take that to the -1/3, that'll give us a distance, a separation distance. So the ratio of lambda divided by the particle separation is going to be given by this expression. Right, so we just take the ratio of those two things. Okay, so we have that. Now, recall this thing that I never actually wrote down. Ultimate jerk move of a professor, but we had set up how we solve for this normalization, right? And it was by integrating the number density from energy equals 0 to energy equals infinity, and then setting that equal to the total number. Right, so if we do that and rearrange it a little bit, I've put it in this way so that part in the parentheses there is cubed. Okay, now let's look at the part in front. It's order 1, right? I mean, it's not 1. It's something over pi-ish, but order 1 meaning it's not 10, it's not 0.1. It's not going to make a big difference. So if we're just doing order of magnitude, what we need to look at is what's in the box, and hopefully you can see that that is, and if you can't, you should be able to move the videos around. That is equal to lambda over the particle distance, right? So I had to put this in meme form. Right, so saying that most quantum states are unoccupied and saying that the wavelength, the de Broglie wavelength, is much less than the particle spacing is really two ways of saying the same thing. So that was the point of saying this, right? So that what we said was valid because of the meaning of this, or the quantum meaning of this normalization, right? So classical statistics are valid as long as that is the case. All right, so once that is no longer the case, then we have to do quantum statistics. And when we do quantum statistics, we have to worry about what type of particles we have. Okay, so we got two types of particles, main types of quantum particles. We either have bosons, which follow the Bose-Einstein distribution. So we write this distribution, right? So this is the probability of a particular energy level being occupied. It's 1 over, okay, there's some normalization, A for Bose-Einstein, E to the energy over KT, and then -1. So for the most part, for bosons, the math actually gets hard if you try and do everything perfectly, but we're looking at big ideas here. So for bosons, that normalization factor doesn't really depend on temperature much. So we can basically set it to 1. And so we get this this simplification there. Now, if you if you look at that denominator there, right, we have E to the energy, right, normalized by KT, -1. So if we think about the limit where the energy is really high, wait, sorry, this is something that helps me to write to say it. If the energy, so if the temperature gets large, No, forget what I was going for there. What we should find is that in the high temperature limit, yeah, this would be the same as the Boltzmann distribution, right? And in the low temperature, then we actually have to do quantum statistics. Our other option for type of particles is fermions. So they follow what's called the Fermi-Dirac distribution. Now, fermions, their key feature is that they obey the Pauli exclusion principle, right? So that means that you can't have two fermions that are in exactly the same state. In other words, the maximum value of this distribution function is going to be 1, right? So it ranges between 1 and 0. Now, it looks quite similar if you just write it to the Bose-Einstein distribution, if you just write it with the normalization there, but there's a +1 instead of a -1. But the other main difference is that the normalization has a strong dependence on temperature for fermions, right? So we can write that normalization as e to the negative E sub f, which is the Fermi energy, which you might recall we talked about when we're doing, you know, the energy levels of neutrons and protons within a nucleus, right? So that's the Fermi energy that becomes important. Okay, so we got the expressions, but it's much easier to kind of see what's going on here if we look at the plots, right? So classical versus quantum. So on the left, we have the Maxwell-Boltzmann distribution. In the middle, we have Bose-Einstein. And on the right, we have the Fermi-Dirac distribution, right? So the Boltzmann distribution is just a decaying exponential as energy goes up. Now, this is at a fixed temperature, right? So at a certain temperature, what is the probability of having a certain energy? So the Maxwell-Boltzmann starts at some value and constant and decays to 0. The Bose-Einstein actually blows up to infinity at energy equals 0. And then the Fermi-Dirac distribution, so there's two plots there, right? So the dotted one is what happens at temperature equals 0. So at temperature equals 0, it's just going to be a step function, right? It's equal to 1 exactly up until the Fermi temperature, or sorry, the Fermi energy, and then it drops to 0. So all states below the Fermi energy would be occupied, and then all states above the Fermi energy would be empty. Once you start raising the temperature, you get a more gradual transition. We'll look at that a bit more closely on the next slide. But now this is for a given number of particles. So what would happen if we increased, if we added more particles to our system? Well, for the Maxwell-Boltzmann distribution, that's just going to shift the curve up, right? So we just have that normalization constant. If we double the number of particles, we double that A inverse, that normalization constant. And so the whole curve would shift up and it would have twice as much area underneath it. The Fermi-Dirac distribution can't shift up, right? Because it has a maximum value of 1. So what happens is the curve actually shifts to the right. So the Fermi energy is going to increase, right? So as you add more particles, the Fermi energy increases, and so that just means it's like well, we kind of drew this picture as we were putting particles in the nucleus, right? You have these energy levels, and if you want to add another one, it has to go into the higher energy level, right? Because everything up to here is full, and then above that, you can put, there's empty energy levels, so you put another particle in there. Well, if you put another particle in there, the energy below which all states are filled is now above that. Okay, so that's how more particles get added. With the Bose-Einstein with the Bose-Einstein statistics, I slip of the tongue kind of gave away what I'm going to go for, but weird and magical changes occur if you start to add more particles above a certain threshold value. So we will be looking more deeply into bosons today. Okay, so just kind of a clearer illustration of the Fermi gas. Now, remember, those plots I was showing before were the distribution function, right? So that's just the probability of an energy being filled, but it didn't take into account the degeneracy, or the number of different ways to have that. So if you multiply by the density of states, which starts at 0 and goes as the square root of energy, again, I'm mirrored, so I guess I should go this way. Square root of increases with the square root of energy for non-relativistic particles. That means that basically you don't have any at energy equals 0, even though the probability is 1. It's just there's not a lot of ways to have 0 energy for fermions, or for any, for non-relativistic particles. And then that's going to increase. But then when you're multiplying by 0, it still drops off instantly. So this is a picture of, there's 2 states there because we're talking about electrons, right? So when we say that the occupancy is 1, well, you need to multiply that by the number of spin states as well. So at 0 temperature, or low temperature, basically, again, below the Fermi energy, all the states have 2 electrons in them, and above that, there's none. Yeah, so this would be like electrons in a metal, right? We can treat the conduction electrons in a metal as if they're a Fermi gas. But then if you increase the temperature above 0, then what happens is the Fermi energy stays the same. But what happens is basically you give some energy to some of those electrons that are below the Fermi energy and excite them above the Fermi energy. So when the temperature is non-zero, then there are unoccupied states below E Fermi and occupied states above E Fermi. But it's more or less, until you get to really high temperature, they're mostly filled on the low end and mostly unfilled on the high end. Yeah, and so this is all the stuff that we're going to do with Fermi gases in terms of understanding, like electrons within metals, or we'll be able to use this to describe white dwarfs or neutron stars. We can treat it fairly well by treating it as being at 0 temperature, right? Because just as an estimate, as long as you don't get well above the Fermi energy, then you can, these 2 pictures are fairly similar, right? You've got a few that are excited above that, but if you're just trying to figure out some basic quantities, you can treat it as if it's at 0 temperature. So this is part of the reason why I say, when I was talking about neutron stars, when I say that they're at low temperature, okay, yeah, it's 1,000,000 degrees, it's low only when you compare it to the Fermi energy, right? So the temperature of a neutron star is pretty close to the Fermi energy, and that's why we can treat it as a low temperature. I'd have to, I haven't read ahead in my notes to remind myself, but I think the Fermi temperature for the conduction electrons in a metal is something like 10,000 degrees, right? So we can treat them as low temperature at any realistic value of the temperature. Okay, and there's the, I forgot to bring up the, that was what I just said about the general behavior of Fermi gases. All right, any questions at this point before we do some specific boson gas stuff? All right. So one type of boson gas that we can do is a gas of photons. And we skipped over this section in, what was it, chapter 3, maybe, about treating light like a particle, right? So some of the earliest evidence for quantum mechanics. So some of the earliest evidence was Planck. He came up with the idea of quantization to describe blackbody radiation, right? So blackbody radiation is the electromagnetic radiation that objects give off just because they're at a certain temperature, right? So like we can describe stars this way, we can describe incandescent light bulbs this way. The reason why, heated metals start glowing red hot and then white hot as they get hotter. We can even describe, the infrared radiation of, people or other, just sort of ordinary objects that we don't normally think of as glowing. We can describe them as blackbody radiation, but the classical explanations for what was going on there didn't work. Right, so the ideal picture of a blackbody is just an empty cavity with a small hole in it, and that empty cavity is going to have electromagnetic waves in it, right? You're going to have standing waves, particles in a box, right? Just like we've done a million times. And then some of those particles will escape. But the thing that needed to be explained was, well, if you have standing waves, of course, there's a lower limit to the wave, or sorry, there's an upper limit to the wavelength, right? You can only have, if I have a box this big, I can have a single standing wave, right? So that's going to be, like an infrared wave or a radio wave or something, depending on how big your box is. But there doesn't seem to be, if you start going into ultraviolet and X-ray and stuff, right? You can just keep putting more and more high energy particles in there because, once you start making that wavelength really small, I can fit anything in there. So it seemed like, it was called the ultraviolet catastrophe, which was, it seems like there should be an infinite amount of high frequency, low wavelength radiation coming from a black body, but we know that's not true, right? We don't instantly get killed by gamma rays every time we step outside from the sun. Okay, so the solution is to treat photons as bosons. So they're going to, we're trying to find, how much energy is in a certain volume of a gas of photons at a certain temperature. So photons are bosons. They follow the Bose-Einstein distribution, but the number is not fixed, right? You can always create and destroy photons willy-nilly, right? They're constantly being absorbed and emitted by all of the atoms that would be making up this black body. So, okay, so if we calculate the number that we would expect at a given energy, right, we have our calculation here: volume times density of states times, in this case, the Bose-Einstein distribution. Okay, so I write that out here. Recall that our density of states here, we have to use the ultra-relativistic one, right? So rather than going up as square root of energy, it goes up as energy squared. So I've got that factor there. And then I've got the 1 over exponential stuff that is what we just stated was the distribution function for bosons. Okay, so what we really want is the energy density, right? Energy U per unit volume. So to calculate energy density, well, we would want to integrate from 0 to infinity. Now we're trying to find the expectation value of the energy. So we would take energy times the distribution function, the number distribution function, and integrate it over all possible energies, right? Oops, I left out my integral in that last part. So this is still, so, okay, so I just took that first line and multiplied it by E, but I dropped the integral on accident, right? So when you integrate over that, I didn't show the steps, but if you do that integral again, it's going to be one of these exponential integrals that you have to look up. It involves pi, always involves pi for some reason. So it's pi to the 4th over 15. You get that the energy density is this, numerical factor. Yeah, wow, okay. I'm going to fix this because there's too many mistakes on this slide. Okay, so I'm updating that. There's still the integral, same limits, and then here I missed some parentheses. Yeah, it's because I made them curly braces. Okay. There we go. Okay. So, using that, I mean, the important thing here, other than getting the units right, but the key factor is that the energy given off by a black body is proportional to temperature to the fourth power. And this was already known from observations. This was known as Stefan's law. And other than the dependence on Planck's constant, right? They just had, a number that was measured. But the Stefan's law was that the energy of a black body depends on temperature to the fourth power. So you can measure that, with a given, heat up a piece of iron to a known temperature and then measure the energy that it radiates, and then increase the temperature and see how that changes. So this was known. So being able to find that from Bose-Einstein statistics is, a good proof or check that it works. Another thing that we can do is take that energy density. So before you integrate it, right? So take that energy density and change it into a function of wavelength, because that's how it's usually plotted. So just with a change of variables, the familiar energy is equal to hc on lambda, inverts that, and then just write energy density. So lowercase u just means energy per unit volume. Then we get this expression, and this is how these things are usually plotted. So this is the intensity, radiation intensity plotted as a function of wavelength for several different, well, it doesn't matter what they are, whatever black bodies you have. So it could be a metal, or it could be a star, which is where this is often applied. So plotting that at different values of the temperature, you can see they're labeled there. You can see not only does more temperature mean more total energy is going to be given off, right? It would be the area under the curve, but it also changes where that, at what wavelength that energy peaks, right? So at 2000 Kelvin, pretty hot, right? 1700 Celsius, which is, I don't know, hot in Fahrenheit. The peak is still going to be in the infrared or the far infrared, right? It's not that close to the visible spectrum, but you start to get some visible light given off. So at that point, probably between 2 and 3000 Kelvin, you would start to say something is glowing red hot, right? Because even though it's peaking still in the infrared, it's going to be giving off a lot of red light. So it's going to, but not that much blue light. And so it's going to look red. And then, as you start to get to 4000 Kelvin, now you're seeing a lot of visible light being given off. Of course, there's still a lot of infrared light, which we feel as heat, or infrared radiation, which we feel as heat, being given off. So you're going to feel that as well. But it would start to have much more broad spectrum. And so we would say things start to glow white hot. Right? And then peaking in the middle of the visible spectrum, green to yellow, sunlight peaks in the middle of the visible spectrum. So does incandescent light. Now, that's not a coincidence, probably. We probably evolved eyes that allow us to see in the part of the spectrum that the sun gives off most of its light. So, that's why tennis balls are greenish yellow, right? Optic yellow. For a while, they started making fire trucks optic yellow, and ambulances, but I don't know. A lot of the ones I still see around here are red, but because fire's red, I guess. But optic yellow is like the most visible color for the human eye. So it's not that, but tennis balls are dyed, right? They're not glowing 5000 Kelvin. So if you just took that expression as a function of lambda and you took its derivative, set that equal to 0, solved for that, you would find the peak wavelength as a function of temperature, and you'd be able to reproduce that plot. And that was also known before quantum mechanics. So it's called Wien's displacement law, W-I-E-N, Wien. And so that was another confirmation of this, this math that it was able to reproduce what was already observed, but explain it for the first time. And so the the explanation of blackbody radiation, along with the photoelectric effect, were really the things that proved the usefulness and correctness of quantum mechanics early on. Questions before we move on? All right. I hear my dog telling me that the mailman is here. Hopefully she can handle it. All right. Now, another interesting thing that we can do with bosons is called Bose-Einstein Condensation. So Jarrett's going to be paying particular close attention here based on his topic. So let's look at, so this here we're going to go to bosons that are non-relativistic, right? So not photons. So they can't be created just out of thin air, and they have a different density of states, right? It's the one that goes as the square root of energy and not E squared. And then you got that whole whole mess of stuff in brackets. So this is what we came up with this on Friday, and we're going to use it now. So now again, I've dropped that normalization for that A for the bosons. And the reason for this case is that we're looking for, we're going to try and look for the maximum number of bosons that can fit in a particular volume. Right. So when we calculate this this integral, we're trying to find the maximum value. So if you had something other than 1 down there, right? If you had a factor of 2, for instance, well, then you'd be dividing by something in the denominator, and therefore you get a smaller number, right? And it can't be anything negative, because that would mean, or anything smaller than 1, because then that would allow the denominator to sometimes become negative, and you can't have a negative distribution function. It just makes no sense, right? You can't have a negative probability. Okay, so to get the maximum number, we let that normalization be 1, and that also makes our life easy. Okay, so we want to calculate n, so we're going to integrate from overall energies. So we've got stuff, right? That stuff in braces. The integral from 0 to infinity of this square root of e divided by this exponential minus 1. So again, just as a reminder of the general technique of what you need to do for these type of integrals, we would do a change of variables. And here I called it x just because we already used u for energy density, so I didn't want to get that confused, but you can call your variable whatever you want. So we would just use, again, as we have been, e over kt is our x, and so we're going to get this dimensionful factor out in front of kt to the 3/2, and then we've got that integral, and it's going to be some number on the order of 1, and we may or may not be able to figure it out. So, anybody have any guesses? Wrong. Okay. It's okay. There's a square root of pi involved. You probably guessed that if you had guessed anything, that there would be a pi somewhere. And then there is this thing zeta of 3/2. That's known as the Riemann zeta function, and it's got some weird properties if it's related to the prime numbers, and I think there's a Millennium Prize related to like figuring out some properties of the Riemann zeta function that you can win $1 million for solving. But we know how to calculate it, or somebody does. It's not a nice looking number, so too bad. You can keep it in there, or you can just put things in decimals. So we get this gross looking thing. Okay, that 2.612, it's actually ... right? It's not going to be an exact value. And then we've still got, I accidentally factored out the spin part from the rest of the stuff. So you could stick it back in stuff if you wanted. And then times kt to the 3 halves, right? So you've got number times dimension full stuff in braces, and then times kt to the 3 halves. That's going to be the maximum value of bosons that it seems that we can put into a container. Okay. Great. What happens though if we try and add more particles, or if we have a gas that has the maximum possible number for a given temperature and we reduce the temperature? Where would they go? Well, let's take a closer look at the energy equals 0 state. So our math is telling us, okay, so we've got our distribution function for bosons as energy goes to 0. That goes to infinity. But that's okay because our density of states as energy goes to 0 goes to 0. So when you're multiplying those two times each other and you integrate, it keeps your integral from blowing up. However, we know that any quantum system has to have a ground state, right? There has to be a lowest state that has particles in it, because we can kind of prove this by contradiction, right? If you had said, well, there's emptiness and then there's the first filled state, then you would just say, well, if there's emptiness and nothing's allowed there, then it's not not physically true, not physically meaningful. So the first filled state is the ground state, and we just rename that, you would measure all your energies from the ground state, right? So the ground state must exist and it can't be empty. So even though our math says that, that from the density of states it goes towards 0, there must be a ground state. So it's not actually empty. There could be one particle there. But if there can be one particle there and they're bosons, then you can put another particle there too, right? Fermions are not allowed. They don't like each other, right? Fermions are social distancing. Bosons are on spring break. So that's basically what happens is the ground state becomes the Florida beaches of spring break, and you can just start putting particles in there. Technical term, you can put particles in there willy-nilly. So this maximum number that we found was actually not the maximum number. It was the number that were in excited states, right? So it's the number of particles that are not in the ground state. That was what we actually calculated, even though we called it Nmax. We were deluded. So the extra particles go into the ground state with no limitations. So the total number of particles then is going to be equal to n naught, the number of particles in the ground state, plus the number in the excited state, which is what we had calculated. Okay, so where does this start happening? Because above a certain temperature, right, there's basically no particles in the ground state. I mean, there might be one, or it has to be at least one, but there's, as a percentage of, you got moles worth of particles and one is in the ground state, it's basically 0. So if we find the temperature where n excited is equal to n total, basically no particles in the ground state, you can calculate what's called a critical temperature. So you basically take, let me go back, not that far. You take this expression at the bottom with stuff, written out, and solve it for temperature, right? And invert that and solve it for temperature. And so when you do that, you get the critical temperature where you have filled all the possible excited states. And that's calculated here. So It's going to depend on the volume, which makes sense. It's also going to depend on the mass of the particle, right? So a more massive particle is going to have a lower temperature where this starts to occur. And then you can also find, so by taking that n total and subtracting the n in the excited state and solving, you can find this nice, concise expression, which is the fraction of particles that are in the ground state. Right, so basically when the temperature is equal to that critical temperature, there are no particles in the ground state. They're all in excited states. But if you're reducing the temperature rather than shoving more particles into your container, if you reduce the temperature, then you're going to get more and more particles into the ground state as you reduce the temperature. So all the particles are in the ground state. They're all in the same quantum state. So weird stuff starts happening. Yeah. So for an ordinary gas, if we take the density of an ordinary gas, it's like 10 to the 25th per cubic meter. So if we calculated the critical temperature for that, it would be about 1 millikelvin, which is cold enough. But a real gas, right? So if you said, well, let's do this, what's a boson? Oxygen is a boson. Helium-4 is a boson, right? Anything with an integral spin in the nucleus is a boson. So, helium-4 is a good example. Well, you would actually create liquid helium if you just kept the density, if you took a tank of helium, like from even just a balloon shop, right? That's somewhat compressed, but not, or actually compressed, so that's going to be bad, right? Denser than it would be at room temperature. But if you try and take that helium tank from the balloon shop and cool it down to 1 millikelvin, it's going to become a liquid before it would ever get into this Bose-Einstein condensate, right? So this is not a condensation in the sense of something becoming a liquid. It stays as a gas. It's just that a lot of those particles then jump into the ground state. So you need the density from a practical point of view, just because real gases do become liquids, about 1 million times lower density for something like helium-4, and it condenses at about 100 nanokelvin. So really, really cold. And that was first achieved. I actually remember reading about this because I was a nerd. Was a nerd, as if I'm not still. In 1995, my family had a subscription to Scientific American, so I remember reading about this. So using a combination of laser cooling and magnetic cooling after doing the normal sort of refrigeration and diffusion techniques, this was first achieved, and then pretty quickly that was awarded a Nobel Prize. So it's named after Einstein, right? Einstein was not alive in 1995. So this and Bose. I mean, well, I don't know when Bose died. Probably was not alive either. But this was 1920s, 30s that this was first predicted and not experimentally observed until the mid 90s. So I didn't, we wouldn't have time to really get to it anyway, but so I didn't prepare sort of like the examples. But what really happens at this low temperature is that all these particles, they go into a single quantum state, so they really act as if they're a single quantum system, and so weird things start to happen because of that. So we'll go into that in more detail on Wednesday, and also do some of these Fermi gas examples. So that's what I had for today. Any questions at this point?
So I just have one question where you said in the beginning, you said find T where n total equals n excited, but in the previous slide it says that the ground state must exist.
Right. So make one of those lines in the equal sign squiggly, I guess. Right. So there'd be like 1 in the ground state at temperatures above the critical temperature, but that's basically 0 when you're talking about a gas of molecules. So yeah.
Cool.
Because if you think about 0 energy, or the lowest possible energy, that would mean no kinetic energy. There really is only one way to have no kinetic energy, and that's to not move at all.